Thank you for the invitation, and it's a pleasure to speak here. Is this open or actually? It's good. So I will start with some motivation or some results we hope to prove. So motivation. So let's consider a number field F over. So I want to just consider some piece of cohomology of certain smooth projective variety over. So this is over F. So I have the Galois action on L-adic vector space over V. So V. So our primary example will be cohomology of certain variety over F. Or suitable twist, Tate twist. So one can consider the so-called Benningsen-Broch-Seymour group. So the dimension of the Seymour group suppose this is irreducible and does not irreducible and the non-trivial Galois pentane. So then the conjecture of Benningsen-Broch-Kato predicts that the dimension of this Seymour group, the Benningsen-Broch-Seymour group, is equal to the vanishing order of the L function. So order of the L function at s equal to 0. So there is a certain dual to take. All right. So this is the conjecture. Okay. What we know about this conjecture is very limited. For example, one consequence of this conjecture is if you assume this Galois pentane has non-negative weight, then so on this side, the L function will be non-zero by trivial reason because it's in the absolute convergency, the range of absolute convergency. So you know this will be we have vanished order 0. So it follows that this left-hand side should be non-trivial. But even this seems to be far from known, except some cases. For example, maybe the result of Caligari, Garrett, and maybe Michael, and a joint motive for Anderson hypothesis for certain prime L. Another example, another consequence of this conjecture, actually the special case I mentioned for the rank 0 case, when this is in the range of absolute convergency, is that another consequence is, for example, if you consider V to be certain tensor product of H1 of a curve. So if X is a curve, I consider H1 and I consider some tensor product power big enough. I do a Tate twist. This is supposed to be, if n is big enough, this will have non-negative weight. And actually, if n is bigger than equal to 2, this will be has positive non-negative weight. So you expect the Seymour group should be trivial, where X is a curve. For example, with genus G bigger or equal to 2. So if you assume this conjecture, you know this corresponding Seymour group should be, Broch-Kato Seymour group should be trivial. This actually has a strong consequence. For example, Mignon-Kim's method, if you use his non-abelian Chabalti method, this would imply the Model conjecture for this curve over a number field. So we don't know much for this. But what do we know? But we will consider the case when this is self-dual. So the theorem we know, we write the following results. So let me consider V come from the cohomology of the theta module of a elliptical curve. So we're E. So we're in a more familiar situation, E is elliptical curve over Q. And if I take a quadratic field K, so K is a imaginary quadratic. Field. So then, theorem is that this conjecture holds for. So then, assume the order of L function is at most 2, at most 1. Sorry. L function. In this case, it's this has the V zeta function. Okay, I'm twisting this. I'm shifting the center. So this is order at the center of the L function. If this is at most 1, so the equality holds. So the conjecture holds. And moreover, in the case of rank 1, so the Shimura group. Okay, I have to put a twist. So V. Okay, actually I don't have to. Right. So V. So this is spanned by the image of Abel Jacobi map. So it's given by the model Wei group, spanned by image of rational points, E of K, in the rank 1 case. So this, of course, this is due to, well, in such a generality, this is due to many people, including Grozagi and Kolivagen. And if you impose certain twist, so this statement can have one can twist. So rank class field character. So rank class. So finite order. So if you twist everything by a finite order character, rank class character, for this quadratic field, rank class character of finite order, you have the same results, but the proof actually requires. The proof is more subtle in the sense you have to do. It's really two cases: one for rank 0, one for rank 1. And in that case, it's really, you need to put it also in the rank 0 case, so in the order 0 case, you have to use Wasberger Bernoulli-Darmon's argument, using congruence. Where they use the fact that certain Shimura curve has a reduction given by has a uniformization by the Drinfeld upper half plane. So by using congruence and certain special feature of Shimura curve. Okay, and in the rank 1 case, order 1 case, you have to also in this generality, you also have to use the result of Yuan, Zhang, the YZZ version of the Grozagi formula. So basically, the two cases are actually by independent argument. But both cases have to use the construction of. So both cases you have to use. So the key construction is the Hingern points on Shimura curve. So on one hand, you make a connection to L function or L values. So by proving formula of Gauss-Zagier type or Wasberger type. So this is one direction. You make such connection. The second thing you do is to make a connection between such algebra figure points on Shimura curve and the Symmetric group. So this is the Kolyvagin type, the Euler system type argument of Kolyvagin. But in this case, in the rank 0 case, you have to do congruence and using certain special feature of Shimura curve in the rank 0 case. So by going to this construction, you can prove the connection between L function and the Symmetric group in the rank 0 or rank 1 case. So this is the triangle we want to focus. And the motivation is to try to see what kind of results one can prove for higher dimensional. So the question is, can one prove something like the theorem I write down for higher dimensional Galois representation? So for higher dimension V. So that's the question, and so what one can hope is, of course, only when V has a certain special property, for example, coming from the cohomology of Shimura variety. So this up here in cohomology of a certain Shimura variety. Okay, again, I'm gonna just focus on the case when V is self-dual. So V is. So I'm gonna looking only at the central point of the L function. So one such generalization to higher dimension is, so one generalization. Is a Gangros-Prasad situation. So this is a Gangros-Prasad. Let's say in the unitary case, where the corresponding Galois representation is of the type if the following form. It's a tensor product of two. So one has say n-1 dimension, other one has n dimension. So dimension. So you take the tensor product, and of course there's more conditions here. So for example, for this has to correspond to automorphic representation, which can be descended to unitary group. So that's the unitary case. So you see in this case, the corresponding L function will be certain ranking stable L function for GON-1 times GON. Oh, same V. So V. So where this. So this is a Galois representation of a certain number field F. So this. Okay, this is not a unitary. This is not a Hermitian space defining the. Huh? Okay, dimension of those two guys are respectively n-1 and n. Okay, this maybe this is a little confused with the earlier notation where we used W to denote maybe Hermitian spaces. So this is the Galois representation attached to automorphic representation. So okay, so you're looking at, because my V is in this case is this Galois representation. Okay, so the L function is the ranking stable L function in this case. All right. Okay. And in this direction, well, one can actually, well, in higher dimensional case, maybe I should have said earlier here, when I ask this question, if you look at this triangle, one can only hope to, well, probably have to modify the theorem for higher dimensional case by replacing maybe the L function by p-adic L function. I mean, L-adic. L function maybe have to be replaced by L-adic version. I mean, p-adic, p equal to L. In the rank 1 case, because even if I have such a connection, I wouldn't be able to deduce the non-triviality So even if I have such equality, certain equality between those and this guy, I wouldn't be able to deduce non-triviality for the cycle class of a certain, in the same R group. So it's better to use L-adic L function in the higher dimensional case.
Sorry, can you? I didn't understand.
So even if I have, so this arrow tells you when you expect to have certain equality between, say in the rank 1 case, the derivative of L function, and a certain, well, in the complex case, it would be the height parent of a certain cycle. But even you have such equality, you only know the height parent of this cycle is non-trivial. You cannot deduce this cycle has non-trivial Abel-Jacobi map. But it would have such non-triviality if you have equality between the derivative of the p-adic L function. Because in that case, the p-adic height, so you have to consider p-adic height instead of Archimedean height. Then you would conclude from the equality of with the L function that you have non-trivial p-adic height, which factor through the Seymour group. So you can get non-trivial elements in the Seymour group. So there's certain unknown conjecture for algebra cycles if you consider the complex L function. But if you use the p-adic L function, you can avoid such conjecture. Okay. All right. So this is the case in the Gann-Grossberg set. You have the L function being Rankin-Selberg. Is Rankin-Selberg for GON minus 1 times GON. Okay, that's the right. Okay, so now the goal of today's talk is to propose a different generalization, alternative generalization to higher dimensional, where you don't have to take the tensor product. So this is sort of more, in some sense, slightly more direct. More direct from the Gros-Zagier formula. So in the following sense, so this is, so this is the rough idea is, so this generalization, the rough idea is to go from the following, starting from the, if you start with the Gros-Zagier situation, where you consider this quadratic field. So group theoretically, so you're looking at the restriction of scalar of K, where K is my quadratic extension. So you look at this anisotropic torus and embed this into GL2 over Q. So that's the Gros-Zagier situation. One direct generalization to higher dimension, or higher, at least in the function field case, this actually works. You can just replace this by, okay, let me say. So you can replace everything by GO2 by GON, for example, GON. Then you do restriction of scalar of GON half. So by choosing a Q basis of K, you can get such an embedding. But of course, the problem is that we don't have a Shimura variety attached to GON over Q or GON half over a quadratic extension. So this doesn't work, but this does work for function field. So this is okay. This idea actually works if you replace number field by function field. For function field. So which was considered by in the joint work with Ji Wei Yun. So okay, so if this doesn't work, maybe we can do something which is usually done in the number field case. GLN doesn't have Shimura variety, but we can try to consider its outer form. So I can consider unitary group, right? So now let me start by describing. So that the goal of the rest of the talk is to define a generalization of the special cycle on the Shimura variety, and then I will describe some results from the local study of those algebra cycles. So now let me describe the Shimura varieties, and then I describe the special cycle. So now let me describe the Shimura variety, or the simple Shimura variety. Well, this in some sense can be considered a Z modulo 2 theory. Okay, you will understand. I will explain what this means later when we go to the next section. So here I have the simple in the sense. So this Shimura appeared in the work of Cordovez and Harris Tanner. And also maybe in Clozel's work. So we consider the following setting. I have a total. Let me consider a total real field. So F is a total real. Total real. And let me consider a CM quadratic extension F prime. CM quadratic extension. So in the Harris-Tanner case, it's actually going to simplify our life if I impose F prime is obtained by F composed with a certain quadratic extension K. So K is as before is an imaginary quadratic over imaginary quadratic. So over Q. So this will simplify, for example, the reflex field for our later consideration. So this is the data we're going to fix. And then I consider a simple central algebra. So B and a star. So this is a simple central algebra with an involution of second kind. So central simple algebra over the same extension over F prime. Okay, you will see the hardest part of the talk is to choose the right notation for quadratic field. So now I'm using F prime over F. Maybe this is not good on the chalkboard because I have to write the prime sign everywhere. All right, okay, simple central algebra over this quadratic extension of say dimension. Dimension is n squared. So n is my fixed number. As F prime algebra, dimension n squared. With the second in kind involution, which means this involution, if you restrict to the center F prime, it induces the non-trivial Galois involution with respect to this quadratic extension. Okay, so that's the data. Then of course you have to, well, to get some Shimura variety, you choose a skew Hermitian form. So meaning eigenspace of -1 for this involution. Then you produce another involution by twist the given involution by this skew Hermitian form. So let's say a new involution to get a new involution. New involution is called sharp, which is the conjugate beta of the given one, the star. So examples. So major examples will be. Let me see some. So the examples. Example is when the central simple algebra is a matrix algebra. So B is n by n matrix algebra over F prime, where star, the involution star is given by by the usual way, by the transpose. Then you apply the Galois involution entry-wise. Here, bar denotes the Galois involution for f prime over f. Okay, should have said this is also required to be positive definite, but this is a nice example for that as well. So then I take a skew Hermitian form in the usual sense. So this is beta is skew Hermitian. Okay, skew Hermitian form. Then you can get a new involution, and from this new involution, I can define the unitary group and its similitude version. So let me define G. This will be G inside B, the multiplicative group of B, such that G times this involution is a scalar. So this is a similitude version. Okay, let me consider everything as algebra over Q. So I want to have an algebra group defined over Q with a rational number. So this is the similitude factor, which give you a character of G to Gm. The kernel is a unitary group, or the restriction of scalar of the unitary group. So G0 will be my. So this is the unitary group. G0 is a unitary group. This is a unitary group with a similitude. Okay. Oops. If you go, let's go to this example. If you do this example, you will get the usual unitary group attached to Hermitian forms. But this formulation using simple central algebra gives you more freedom to consider to get a unitary group. I mean, they are inner form of those unitary group attached to the Hermitian spaces. So I should remark also that so compared to the Hermitian unitary group, what do you get by doing this construction? So remark is that the condition for the existence of such involution. So for the existence of such involution of second kind, it imposes non-trivial condition on this central simple algebra. So locally, if I consider a place V, if V is a place of F, if it's inert or non-split, if this is non-split, V non-split in F prime, say the unique place is W, so then BW, the localization has to be the matrix algebra. So it has to be the trivial. I mean, Hasse invariant has to be 0 for this. So that's the condition at such a place. If V splits in F prime into two places, W and W prime, then the condition is that the Hasse invariant at those two places, they should be opposite to each other. So one is the opposite algebra. So you switch the order of multiplication, you get a new algebra. So that's the opposite algebra. So this is, yeah, right. So that's the condition you need. And this is actually a sufficient condition for the existence of such involution of second kind. So in other words, for those non-split places, you don't get anything more than the usual unitary group for Hermitian space. But for the non-split place, for the split places, you are allowed to have, for example, you are allowed to take this to be division algebra. For example, you can take division algebra. Particularly, if you take division algebra of Hasse invariant 1 over n, you will get a Shimura variety where at such place your Shimura variety will have a uniformization by Drinfeld upper half space.
You also have some
So
parity condition to get the signature. Some of the invariants have to be.
For this, I think this is okay. I'm not talking about more.
You haven't said what the signature is. So
Right. So for this moment, I'm just saying for central simple algebra, for such central simple algebra to have involution of second kind.
but you just also said the Drinfeld
Okay.
stuff.
All right. Okay. Right. So I haven't even defined the Shimura variety, so I think I realized I was jumping. Okay. All right. So now I have to impose condition on the unitary group. So I want to make sure. So I will impose the condition on the signature of the unitary group. So the unitary group, the real point, should be should be compact at one all places except one. So for all places except one, so for one distinguished place, if you choose, it should be compact. Should be the compact unitary group, and for the remaining one, it has signature 1 over 1 for the distinguished embedding. Okay, so all right. I mean, there should be really more careful definition of the Shimura data, so one get really a PL type Shimura data. But maybe this is less important for the moment.
This is the
So
assumption,
G.
right?
Huh? Say that again.
This is the assumption.
This is assumption, right? This is assumption on the Archimedean part of this. Okay, so as I said, one should be more careful to even upgrade this definition into a PL type PL data. So one can design by choosing more data. For example, by choosing such that the reflex field in general it's quite complicated, but one can make a choice so that in the Harris-Tanner case, so in HT case, this is given by it's this quadratic extension embedded into C with a distinguished embedding. So in this case, the reflex field can be simpler, but in general, if you randomly choose a certain same quadratic extension, it could be very complicated. All right, so at this point, if I choose certain place, maybe let's for simplicity let's only consider the Harris-Tanner case, so I don't have to worry about the reflex field. So if B is a division algebra,
What is Harris-Tanner case?
it means this quadratic extension here, this case, where this same extension is given by this total real field composed with imaginary quadratic over Q. Instead of arbitrary, this same extension could be very, very general. But if it's obtained by a total real composed with a imaginary quadratic field extension of Q. So everything is induced from Q in some sense, from this imaginary quadratic field over Q. So division algebra with Hasse invariant 1 over n. So you will be able to get. So you can get. Also, I didn't specify the level structure, so you put the level structure to be the maximum one at this place, the Shimura variety, which is compact. So compact. And it has Drinfeld uniformization. So this gives some hope to run the argument of congruence and level raising, which was used by Bertolini Damron to prove the rank 0 case of the Broca-Kato type conjecture. So this gives you some hope you can do that. Where if you consider the unitary group attached to Hermitian form in the classical sense, where you can never have such situation. So this is one advantage of using this simple central algebra construction. All right. Okay, so this finished this introduction to this Shimura variety. So now let me introduce the special cycle. So that as I just erased, it's just by when I replace GLN by this outer form, the unitary group, I should also do the same thing for this subgroup. So I'm gonna do. So this is a special cycle. So I can give another title. The last section was called theory of Z modulo 2. So now it's theory of Z modulo 2 times Z modulo 2. Okay. Where Z modulo 2 was the Galois group for this quadratic extension in the last part. So now I'm gonna produce this biquadratic situation. So I have again I already have a total real field and a same extension f prime. So now let's consider another quadratic extension. Let's write out E. Okay, this may be the place where disaster start to come because I'm having two quadratic extension where E and f prime. So I take the composition. Let's call it E prime. Well, okay, it doesn't really have to be a field extension. It's for the moment it's quite arbitrary. So its Galois group will be Z modulo 2. Over the base field. Okay, that's the situation we want to consider. Okay, now to continue with the Shimura variety, I have to assume this is a totally real. So assume E is totally real, and it's given by embedding into B as F algebra, or the same thing as saying E prime embedded into B as F prime algebra. So F prime algebra. Such that B is a free module. If E prime is a field, this is automatic. But if E prime splits as two factors, this is a requirement. So B becomes a free module over E prime. Also, I'm going to assume this embedding is compatible with the two involution we already had. So compatible with the involution. Star and sharp. So that I can define a subgroup. Okay. So with this data, we consider B prime. So B prime is a centralizer of. So it's natural to do this because I have embedding of algebra E prime, which is commutative. So I take the centralizer of this algebra in B prime, namely those elements which commute with all Meaning those two involutions induce trivial, well, induce the non-trivial Galois involution of what?
This side has 3 involutions, which are 2.
So this embedding, require that this embedding is compatible with this involution, meaning the following. This involution induces the non-trivial Galois involution on E prime with respect to, for E prime over E. Okay. Or the same as saying E is fixed by, it's the same as saying E is fixed. Maybe this is easier. So involution acts trivially, trivially on E. Okay. Namely, beta commutes with all elements in E. All right. So I take the central leg. Yeah.
Do we start and sharp or start?
And sorry, both. Okay. So star and sharp. So maybe the 3 involutions. Okay. So, right. Okay. I have this compatibility. So then I take the centralizer of this guy. So you get a. So this will be a. So this is a central simple algebra over this extension field. Central simple algebra over E prime with a lower dimension, with dimension. Okay, actually my assumption already implies n is even number now. So n is the existence of such embedding implies n is an even number. So E prime of dimension as E prime algebra is n square, half of n square. So that's the situation you have. So you should really think of this as the outer twist of GLN. This embedding GLN half of quadratic extension inside GLN of the base field. So this is the situation I have. Then I can define. I can do the same definition. Maybe I can just use here. I can recycle my diagram here. So without giving you too much, without repeating too much. So I just define GH to be, this centralizer B prime. Maybe prime is not a good notation, but so I get a subgroup H. It's the same definition with just consider this subalgebra B prime. So overall, I get H embedded into G naturally, and also its corresponding unitary group G0. Okay. All right. So that's the special cycle I want to consider. Okay. I mean, there will be induced Shimura data. So, and I can upgrade this into embedding of Shimura data. G and HG. Okay, I should have also said that this Shimura variety attached to G has a modular definition by classifying abelian varieties with action by B or maybe B offset. And here you have same thing for H. So everything can be made into a modular space. All right, so this is the special cycle I want to consider. Maybe I'll give you an example. So to indicate, namely the case when n equal to 2. So what are the groups in this case? So here I have two quadratic extension, but since I have a Galois group given by z modulo 2 times z modulo 2, so I know that there is a third involution whose fixed point, whose fixed field. Let me write it as M. Okay. As you see, like I said earlier, the problem is to choose notation for quadratic extension. Now I have 3 quadratic extension. All right. So now I'm going to tell you what are the groups here. So G. So in this case, the algebra, central simple algebra B, can be obtained as a base change of algebra B0. Let's say over Q. Let's consider the case F equal to Q. So I don't have to worry about the similitude factor being Q or F. So this is central algebra has to come from base change. Then the group G, so the bigger group G, F prime is K. Yeah, right. So say F prime is K. Okay, right. K is my imaginary quadratic field. So in this case, I would get B this simple central algebra over Q times K cross divided by the diagonal embedding of Q. And H is given by this third intermediate quadratic field times K cross divided by the same diagonal embedding. Okay, so you can see that this pair, this group embedding, is given by this induced embedding M. There is an induced embedding M into B0, and you see that this pair is not, well, there is a common factor, which is in the center of the two groups. So if you ignore this part, you actually read it. So this pair H and G is pretty much like M cross inside B0 cross, which is the case we consider in the Gross-Zagier case. You have a anisotropic torus inside an inner form of GL2. So in this sense, this is a generalization of the case of GL2, but you're doing this double twist. All right, so now let me say it again. The real point of H0 will be of the form, it's replace n by n half. So it's the same formula, but changing n to n half. What? Only one place where this is non-compact. Right. Okay. Right. So let me move to. Okay. So that's the global. That's the special cycle we want to consider. Well, maybe I should also say the special case. The special case where
could you raise the previous board, please?
the board. Yeah, sorry. Let me keep those two boards because then. Okay, it's a little complicated now to describe what in this triangle right in the beginning to establish connection between those cycles and L function. So one, okay, maybe I should never use this board. So I'm gonna just write. So one can do a relative trace formula. So to connect to L function, connection to L function. So one has to use certain relative trace formula. But I actually realize it's kind of technical to describe globally because as you say, I have this double biquadral extension. But instead, what I'm going to do is to do the local. So I'm going to describe the local situation. So the local situation, which means I'm going to describe some orbital integrals that will be used to study the local version of this cycle. By local, I mean I look at the local modular space of p-divisible group. So in this situation, there will be essentially two non-trivial cases. So I'm in local situation, unramified situation. So namely, I will consider. So now I'm going to fix everything to be local and periodic. So periodic. Actually, even just for safety, let's say p is big enough, so bigger than n. So I have all those field extension will be unramified. which means there are really essentially 4 cases, right? Because there are only 2 quadratic extensions being unramified over F, and depending on, it could be ramified, split or inert. So you have 2 times 2 4 cases. So there are only 2 cases which are, in some sense, non-trivial. So I will study those 2 cases. So let me describe those 2 cases. The first case is, so this will be section 4. So local theory. So the case 1, which is when, which is the case when this is split. This is split. This is non-split. So I write down the group. So I write down the group. So in this case, so this is local situation. So F prime is F times F, and E is inert. Okay. So this is the situation. So then the corresponding group, so G0 will be really just G O N F. Okay, I'm just writing on the points. And H0 is G O N half of E, which is the quadratic extension, unramified quadratic extension. Okay, I will consider the orbital integral of the following form. So if I consider a function on G0, so we look at the orbital integral where consider any elements G, which is a double coset, G0 modulo H0 and H0. I look at the orbital integral, so defined in the usual formula. So by the way, this case was essentially, already showed up in the case of in the thesis of Jacquet's former student. So this is something which was studied like 20 years ago. This orbital integral. Right. Yeah. Go. What?
It was Goal, right?
Goal. Right. Goal's thesis was study this part. So I have H and H prime and DH prime. Okay, I have to, again, there's so this case is there's non-trivial stabilizer. All right, so this is the case. Let's study this orbital integral. So on the GLN side, well, Goal also has a study, but I'm actually using a different one, a variation. So I'm gonna tell you. So this will be used to study the local, this special cycle in the local situation. But I also have to tell you what will give you the L function. So on the other hand, I look at G prime, which is GLN of this extension E, and H1 prime given by GLN of F. GLN half of E times GLN half of E, where the other group is given by GLN F, but I'm going to also put a quadratic character of the second guy given by this quadratic extension. Is that if you take the determinant, you apply this quadratic character attached to this quadratic extension by class builder theory. So then you look at the orbital integral. It's the same formula, except we insert this guy. So you get orbital integral. So gamma, so function phi, and with s variable. Okay, maybe I shouldn't write it. So or maybe H1, H2. So there's also a way to put s variable for the first guy, then put a quadratic character. There's also a non-trivial stabilizer, but the stabilizer would turn out to be the same as some of those stabilizers. All right. So what one can prove is that So first of all, one can prove some fundamental lemma-like statement. If you look at this, if you take the identity in the Hecke algebra, spherical Hecke algebra, then you get identity between those orbital integrals. So here, it's a fundamental lemma-like statement. Namely, so okay, first of all, you can compare orbit. So for elements in G and the elements in G prime. So then you have identity, okay, up to certain explicit transfer factor. So G identity of G0 of O of F is equal to, so up to sine orbital integral of gamma of identity function of G prime of O, then then S equal to 0, so S variable equal to 0. Okay, so this is something one can do. So then, of course, you want to move to the derivative of the orbital integral and try to compare this with a certain intersection number. And what are the intersection number? So here, so one can now consider the local version of my spatial cycle. So local version of local version of the spatial cycles. In this case, it is actually the following. So if I consider Lubin-Tate space, so let's consider N. This is a Lubin-Tate space. The deformation space of height n one-dimensional p-divisible group. So deformation space. Okay, let me just write it. So this is it's isomorphic to a formal spectrum over the maximum armor extension and take a completion of f. Then you put a formal variable t1 tn minus 1. So this is a formally smooth over this integer ring. No, this is the case where I have G O n. It's the case the groups are G O n. Here. No, the other case I consider you have to take, like what I said. It doesn't work if you take a unitary group as the second group, because the stabilizer will not match if you do the other one. The stabilizer have to be the same type of torus. So then I can take, so this is Nn. For f, I can take n half, but for this quadratic extension E. So it will be a Lubin-Tate space for this quadratic extension. So it's a deformation space of one-dimensional p-divisible group. The formal p-divisible group of one dimension with height n. Here is n half, but for this with OE action. So it's Lubin-Tate space, and this is of half dimension. Okay, I should use different notation t1 tn half minus 1. Okay, so then there's also natural embedding here. So you can put. So in this case, so I have you can define the intersection number G, where G lies in in this division algebra of sine 1 over n, which acts on this Lubin-Tate space, or maybe the integer ring, because I'm only looking at the connected component. So this is the division algebra of sine 1 over n. So I consider this intersection half of E G transpose translate. So this is the intersection number, and then the conjecture is that. So this is, in some sense, is a linear version of arithmetic fundamental lemma. So a linear version in the sense I'm using linear group, not a unitary group. So this conjecture is this is equal to a derivative. So when gamma matches to G of the orbital integral, where I introduce over here G prime of O and S equal to 0. So it's the derivative. Okay, this we well, I should say that what's known in this case, definitely in the case n equal to 2, that's the Gros-Zagier situation. But in general, so the phases of Li, so Cherry Li, so he actually computes all the intersection number. He already has a formula for the intersection number, but for the moment, this will Li give you a formula for I of G for the intersection number in all cases. But for the moment, it's not known how to make this connection between his formula and this derivative of orbital integral. So, all right. So now I have the linear case. The rest will be will be sort of parallel to everything here. So let me. Maybe I'm running over time. So let me just say that the other case, I will have a unitary group, un and un half times un half. So you will consider G or n. So you will change the triple where it's the same except here I have to change this to unitary group or the unitary group with the same unitude. And I have the same story except in that case I have to stabilize everything. So the orbital integral doesn't make so there's a stability issue for the orbital integral for the orbit because the stabilizer will have non-trivial first cohomology, and I have to replace the Lobin-Tate space by the unitary version of the Rabo-Zink space. And what one can prove is fundamental lemma-like statement. What one cannot prove is this conjecture. So there's a unitary version of this conjecture. And what one can prove is that this conjecture is equivalent to, so in the unitary case, is equivalent to the case of the conjecture of Kodaly-Rappaport for the local density. So where they consider the special divisor intersection on the unitary version of the Rabo-Zink space. What I can prove is this unitary version of this conjecture is equivalent to that conjecture. So since I'm running out over time, so let me stop here.